I want to welcome everybody to National Infertility Awareness Week. I'm a fertility clinician. Alan Horsager is the CEO of a company that is working on the genetics of sperm, specifically the epigenetics of sperm. I'm a clinician. I used to be a professor, and now I'm in private practice. But I have a very deep scientific interest in furthering the field. And Alan came up to me once and said, we think we can figure out about sperm health and human health and fertility by looking at epigenetics. So what the hell is epigenetics is the first question. And I'm just a clinician, but I've written a blog on this, and if you want to, so it's called The Real Reason We Are Who We Are. So I just want to explain it quickly. But there's genetics, which is what, say, for example, Alan and I are about 99.5% identical genetically, and we're about, men and women, about 98.5% identical genetically, and in fact, we're about 50% identical genetically to bananas. But we are not bananas, and I'm not Alan, and we're not women. And the reason why we're different, despite being so identical genetically, is because of the word epigenetics. And epigenetics is not the sequence of DNA that is the Watson and Crick model. It's actually a parallel universe. And it's marks on the DNA. It's the way the DNA is sort of coded to either become protein or not eventually. And there's several systems in place that the body has to hide DNA from being made into other things. And this is one of those systems that is specific in sperm. And Alan has studied this for years, and I've been interested in it for years. It's sort of the latest and greatest thing after DNA and genetics is epigenetics. It is probably the basis for many cancers. It's the basis for autoimmune disease. It probably is the basis for schizophrenia and autism and other neurodegenerative disorders. And it describes why a nose is a nose and an ear is an ear, despite the fact that those cell types are identical. It's why organs are organs that they are. I think that's what we're talking about, right, Alan?
It is indeed. So a little bit about my background and how I got to this field, because it's a little strange, actually. So my background, I'm a PhD in neuroscience, and I actually became very interested in this through a conversation. This is where it started with Andrew Smith, who's a computational biologist at USC. And he's one of the co-founders of Episona as well. But I was asking him about things that he was working on. He said, I'm doing this work in epigenetics in sperm, which you know a little bit about now. And he was looking across different species. But in the humans, in some of the samples, he saw some abnormalities in a gene region that was thought to be very important for neurodevelopment. And my question was, could you actually use that information to try to predict disease outcome in offspring? And so this coming from a neuroscience perspective, that's what got me interested. But that's clearly a very difficult thing to do. And so I started to think about it more broadly about other opportunities in epigenetics. Is there more information there that we can use to help understand disease and other aspects of human health and disease? And so started digging around, immediately came across work from Doug Carroll, who's been working on this. He's a professor, he's an andrologist from the University of Utah, been working in this field for probably several decades, but certainly in epigenetics for probably a decade. And he has done a lot of work looking at how changes in this epigenetic profile can impact both fertility and early development, specifically the development of the embryo. And so we started to dig into it a little bit and ask whether there was an opportunity for developing a diagnostic test for fertility based on the epigenetic profile. And that's what we've been doing for the last couple of years, which I can dig into here.
So, but I just want to say I'm really happy you went from studying the real brain to studying the true brain of men.
It's all connected. It's along the axis, right? So I think one thing I'd like to talk about here is, so the audience, I think, is kind of a mix of both physicians and patients. So I think I want to to make sure that we're speaking to both groups. But Paul, I would like you to describe, if you can, why do we? So the first question I asked Paul when I first met him and talked to him about this is, do we need a better diagnostic for male infertility? So maybe you can start there, Paul, and that can help frame the rest of the conversation. Why bother with it? Actually make any sense?
Right. So do we need a new mousetrap? So
Yeah.
the semen analysis is the single best measure that we have to predict male fertility. But unless it's 0, it's a terrible predictor of true fertility. Remember, fertility is not a semen analysis. Fertility is the ability to conceive. So it's a 50 to 60-year-old test. It hasn't changed much. We've argued about what's normal and what's not, but it hasn't really been, it's been what I would call a blunt instrument in the ability to dissect out fertile men from infertile men, or to figure out why something may be unexplained or explained. Of course, unless it's 0, which is true, sterility is truly an infertility problem. It's been really not very valuable in most cases, and it's nice to have a razor sharp marker. A couple of other tests. So the other thing it doesn't do as a descriptive measure of semen, which is essentially putting order in the universe like counting stars, which may never have meant to be counted, is it doesn't tell you anything about how sperm function except motility, but it doesn't really tell you how well they work. So when Alan approached me with this concept that there's something that looks deeper and maybe it can describe how good sperm are, how well they work, or if they're actually truly fertile sperm or just bystanders, I went around and asked some prominent figures in the field a simple multiple choice question, because I was unsure of what its potential would be, either as an epigenetic test of sperm. And I said, if you could come up with an epigenetic test of sperm that was reliable and could tell you something, what do you think it would tell you? And the options were A, whether a sperm is a fertile sperm or not, whether a man is a fertile bee, whether a man is fertile or not, with that semen analysis. C, whether that sperm could work with simple technologies like IUI and be successful. D, whether it would predict fertility with IVF. E, whether it would predict the ability of embryos to develop well in a dish after IVF. And what am I on? EF, whether it would predict a successful pregnancy or miscarriage. G, whether it would predict any consequences to the child in health, because we know that epigenetic profiles can predict some awful things. And would this maybe predict the health of the child? And then I think the last one was G or H, was none of the above. And there was another one, all of the above. And everyone chose all of the above. So that's what we think we have with this test, is we don't even know its potential, but it certainly could do any one of a number of things. So far, it's been studied very specifically to try to assess its value for a couple of those things.
Yeah. So maybe I can talk a little bit about the goal of the test and what data we've acquired thus far. Maybe that'd be a good next step. So I agree with Paul. I think that epigenetics holds a lot of promise. There's a huge opportunity to, it's an entirely new window into looking into human health that we really haven't dug into before. There's a lot of diseases and disorders that we've assumed are genetic in nature because they're heritable, right? There's an increased risk that someone will develop those diseases based upon the profile of their parents or their grandparents and so on. But the fact is, we've not found anything in the genetic profile. So that suggests that there might be some other heritable element, which, now that we know a little bit more about epigenetics, really lends itself well to that as a possibility. So with this test, I mean, one of the things that we are very interested in is understanding fertility. And so the first question that we tried to address is, can this test actually, this epigenetic test, which we call SEED, can SEED predict?
SEED or SEEP?
SEED, S-E-E-D. And so can we predict fertility status? So what we did is we took men from that were going through treatment with their wives at a fertility clinic, going through IVF, where both the male and the female have been worked up. So men went through the standard semen analysis. Many of them went through DNA fragmentation, which is exactly what it sounds like for those that don't know. It's looking at fragmentation rates in sperm DNA. And then the females go through a battery of, upwards of like 8 different tests. So there's substantially more information on the female side. Female factor in these cases was ruled out. We were left with about 127 men where the infertility was likely to lie. And then we compared those men to fertile donors. These are men with normal semen parameters, known fertility, they've produced offspring. And so we compared those two groups. So to kind of summarize, can we discriminate between normal fertile donors and men that have fertility problems?
But the infertility men had normal semen analysis.
Well, most of them did. Or half of them did. And all of them did have sperm present, right? We couldn't look at anyone that was azospermic, for example.
Right, sure.
Half of them had normal semen parameters as defined by World Health Organization. And we could discriminate between those two groups very well. And so in the study, we had 82% sensitivity, and I'll describe what those mean kind of to most people, and then 97% specificity. So what that says is that out of 100 men that have a fertility problem, we can recognize 82% of them. And then the 97% is out of all fertile men, we can recognize 97 of them. So very accurate test in that regard. And also the second part of that was looking at embryo quality. So could we predict the quality of the embryos before they go through IVF by looking at the sperm epigenetic profile? And again, this is very specifically DNA methylation, which means methyl groups that bind on top of the DNA. It's one of the several different epigenetic mechanisms. And whether we could predict the quality of the embryos. And in those cases, in about 50% of the cases, we could determine whether there was going to be poor embryo development. And again, the specificity is very high. It's a specificity of 98%. So this was our retrospective study, and what we're doing now is a much larger validation study. We're nearing completion. We actually have the data in hand from several hundred subjects through about 10.
Alan, let's take a minute and just recap those findings, because you got scientific on us.
Yeah, fair enough.
So you're saying that it's a powerful tool and it's precise and it's accurate because it could distinguish between fertile sperm and infertile sperm.
That's
sperm from fertile men versus infertile men.
That's correct.
And
this is independent of the semen analysis, right?
Right.
So I think one thing that we should mention here too is that in many cases, in like up to 25% of cases, there are couples that have what it's called unexplained infertility, right? Where everything looks normal, but we don't know what the problem is. And so I think that's what many of these patients that we looked at represent, is those cases.
Okay, and the other part of the study, this is the retrospective study of data and materials that were collected before, is that when you looked at the sperm, you could predict the quality of the embryos that they would generate from IVF, be good or bad, which is a very important thing. It's a very important phenomenon to address called dissolving embryo syndrome. Which embryos are going to do well and which ones aren't. You looked at the sperm and the embryos and the outcomes and correlated them, and they correlated very well.
Yes, that's correct.
All right.
That's correct.
But that's not enough because that's older stuff. So you now have a prospective trial where you're actually collecting samples as people are going through these technologies, and you can design it more powerfully.
Right. So I think what's very important is to do a prospective study where you have people coming into the clinic. You don't know what their status is in terms of their fertility status, and you don't know what kind of treatment they're going to go through and what the outcomes are going to be. You collect the sample before that, they go through their treatment, and then look at them after. And so that's what we've been doing over the last year and a half.
So in this study, you're looking at the ability, you're not looking at natural pregnancies and natural fertility. You're looking at assisted reproduction, and you're looking at IUI. So is the epigenetic profile of sperm predictive of IUI success? And is the epigenetic profile predictive of IVF success? You're looking at embryo quality, embryo development. Those are all the features. So on
So
this list of A through G, you're capturing about half of it.
yeah, so I would say that that is where we're going, a lot of that. There's still lots of work to be done, but I think the first question of recognizing whether there's a factor or not is what this test does even when the semen analysis looks normal. And then secondly, there's a substantial amount of information about which genes appear to be abnormally methylated, or they look abnormal from an epigenetic standpoint, and what they're important for. So, as an example of some of the samples that we've looked at, there are genes that are very important in regards to oxidative stress. Also in the acrosome reaction, which for people that aren't familiar, that's when the egg and sperm connect and the sperm can drop off its DNA. So if they can't make that connection properly, it's hard to fertilize the egg. So we recognize that can be a problem too. And so this type of information can be used to then guide the treatment, right? If you start to understand, well, there's a problem, and then B, what might be causing the problem, if you can have that information, then you can start to guide the care better, right? So that's what we're trying to do. Not just tell you whether there's a problem or not, but what might be causing it.
How many marks are there in the genome? Are there millions of marks? And how many did you look at, and how many do you think are important?
So I think, to kind of give you a rough estimate, there are around 27 million regions where there's methylation on the genome. So, and that's across the genome. Now, what we're looking at 485,000 of them using some technology from Illumina. And we're using a subset of those to make this prediction. So we're using hundreds of them, and which encompass several hundred genes. So we're looking fairly broad.
Yeah, so this is kind of technology that is, informatics-based, massive cluster analysis. This is new biology. This is not something that could have been done 10 or 15 years ago, maybe 20 years ago, not done. But this is pretty sophisticated informatics and systematic biology or systems biology.
That's correct, yeah. So I think what we're trying to understand is that there's this entirely new layer of information. Well, it's always been there, but there's this new layer of information that we've just recognized, this epigenetic profile. We're trying to read it. We're trying to read that information to understand what might be going wrong, and in this case, in fertility.
Yeah, and I think that a test like this is totally different than anything we've ever seen, and it has the potential, more potential to explain many cases of currently unexplained infertility. About a quarter of human fertility, at least, is unexplained. That means nothing's abnormal on any evaluation, like any of the routine stuff for men, a semen analysis, or any of the routine stuff for women. Yet we know there's a problem and they're not conceiving. And then we also know that some couples look, why are they doing poorly at IVF? Everything seems fine, and everyone blames sperm, or they blame eggs, or they blame this or that. And this is going to actually we're going to be able to point fingers at things. And it's nice to be able to blame sperm, because hopefully we can do something about it too.
Yeah, I think the problem has been that the sperm have always been thought of as just a vehicle for delivering DNA, and I think it's much more complicated than that.
Yeah, right? Sperm are people too.
They've been just ignored through the years. So I don't know if there's any. Maybe we should take a moment. I don't know if there are any questions. Maybe there's.
It's a good time for questions.
Yeah. Do we have any questions right now? Okay. So it looks like we don't have any questions at the moment. So let me ask you. I have a question for you, Paul. Of the cases of unexplained infertility, which there are many, and you said there's about a quarter of all cases seem to be unexplained. How much of that is female-driven or male-driven, or we just don't know? I mean, I think the right answer is probably we just don't know. But if you were to make a hazarded guess on where that problem probably lies, where do you think it is?
To date, I would say that most of unexplained infertility has been ascribed to women, because we haven't had the tools to blame men.
I see.
And so that has always been, that's too bad, because, female age, because the fertility potential of women changes so quickly over a 10 or 15 year period, where we don't believe the change in male fertility changes that much over that same time period. We've always said it's more robust, but, I think there's enough data coming out from Carol's work that epigenetic changes to sperm could occur as men age too, and not only as they age, but as they get fat and as they eat poorly. And so what is exciting to me is that this is a mechanism by which your health can affect your fertility, which is what the National Institutes of Health, we just met about it last week in Washington, talking about the relationship between health and fertility and health. And we've always ignored a man's lifestyle, but this could be the vocabulary of which we could speak about how his lifestyle, dietary habits, lifestyle issues, smoking could affect his fertility in a very substantial way. So this to me is a keyhole into a whole other universe, I think it's going to be. I really do. You got something good here, Alan.
Well, it's in no small part to you as well. You've contributed significantly to this. So one thing, a couple things, just to step back. You brought up this idea that the environment and health and behavior, our activities can impact fertility and aging too. I just want to kind of point to the studies on that. So when you brought up Carroll, you're talking about Douglas Carroll at Utah. He did the study looking at sperm in men at essentially day 0 and then 10 years later, and these same men, and he was looking at changes in DNA methylation across the epigenome, and he saw significant differences, both globally and locally. So in the global sense, there was increased DNA methylation, and then locally, it appeared that there were changes in genes that were very important for neurodevelopment, particularly had been implicated in schizophrenia and bipolar disorder, which is, again, very intriguing to me. There's also another interesting study that came out fairly recently this year, looking at what happens to the sperm epigenome as a function of significant changes in weight. So there were guys where they measured the sperm epigenome, and then they went through, they were men that were significantly obese, went through gastric bypass surgery, and then they measured the sperm epigenome again 2 weeks later, I think a month later, and then I think 6 months later. And again, very significant changes across the genome as a function of that. So I think that, and there's probably a dozen papers out there now that kind of show these environmental factors, behavioral changes can ultimately lead to very large scale and very dramatic changes in at least DNA methylation and probably other epigenetic mechanisms as well.
So it's organic and it moves around. So I have a question. What about, where are we, what's the test we're talking about? Is this one test? Is it, how is it done? Is it hard? Is it, expensive? What do we know?
So
you have a box that shows it. Do we know, what does it look like?
This is the box. Where
that's nice.
This is your sample collection kit. I think it has all the details. So you get this at your physician's office. You can take it home, collect a sample. You got instructions here, and you just collect in a container, and you just seal it back up, double-sided tape, drop it in the mail, prepaid shipping, and that's it. So in terms of the actual test, we're still, just to be clear, we're still in validation mode, but we expect that to be done relatively soon, and we would likely introduce this test later this year. I think that's all I'll say about that. But the way it would work is you get the kit from your physician, you take it home, provide your sample, we analyze it, and we then generate a report that goes back to the physician, the ordering physician, and the patient can then go and review it with their physician at the end of it.
So one of the things that's unique about this test that I think is that when you send sperm for testing, it has to be frozen and carefully, and handled very carefully. But this, what we're measuring here is so robust as marks on DNA that, am I wrong? You could leave it out on the sidewalk for a week or two and it'd still be okay. Is that right?
We're looking at Neanderthal, not us, but as a scientific community, we're looking at Neanderthal DNA methylation.
Neanderthal?
Yes. So it's
they haven't ejaculated in a couple of 100,000 years.
That's right. I don't know it's sperm DNA, but I know it's definitely it's DNA methylation.
Oh, okay, good.
Yeah, it's actually very stable. So
it's a very robust test. So if you mailed it to the wrong address and then it got sent over, it'd still be okay. There's no test like this right now. Everyone treats sperm, it's got to be alive. It's got to be within 24 hours. This is a very hardy measure that is resistant to, well, like the post office, right? This gloom and speed of night and sleet and right.
Yeah, so dramatic temperature shifts don't seem to impact it at all, which is very good news. Yeah, so it allows you to just ship it at ambient temperatures, and we've seen exposures up to 130 degrees, and it's just been just fine. So I think that's an important point. I think it's this test is about providing a substantial increase in information while at the same time providing an entirely new layer of convenience for both physicians and patients, for that matter.
So if you want to ask a question of us, audience, you can add questions to the chat module, probably on the right side of your screen, or on Twitter, and use the hashtag #epigenetics. We'd love to hear questions. We want your questions now.
There are a few questions.
Good. See, that works really well.
So we have a question. Do the sensitivity and specificity numbers hold if you have normal semen analysis parameters and those with abnormal parameters? So if I understand this correctly, Mark, I think what you're asking is are there maybe two things? Yes, the sensitivity holds if the semen parameters are normal, that's what we showed in our retrospective study. And also, we don't see any significant differences in our sensitivity and specificity for people that have normal semen parameters and abnormal semen parameters.
How about maybe the other question is there any correlation between the you don't have it yet, but is your gut that there might be a correlation between certain epigenetic patterns and certain semen analysis abnormalities?
Yeah, I think that's likely the case. We don't see it with our test right now. We're not looking for it. We're really focused on trying to understand problems that aren't recognized with the semen analysis. But so there was work done by Peter Laird's group at USC that looked at this, looking at epigenetic changes as a function of how well it correlated to the semen parameters, and they did see stuff. So it definitely exists. But right now, we definitely see things that are above and beyond the standard semen analysis. And I'll take it one step further. In that study, we actually did a gradient purification of those samples and looked at them pre and post that gradient purification. And we can still see very clear epigenetic abnormalities, which allows our sensitivity and specificity is well maintained even after purification. So it's not just that we're looking at dead or abnormal sperm. Those epigenetic abnormalities seem to be carried through to the seemingly normal-looking sperm as well. So hopefully that answers your question, Mark. If you don't think so, please jump in and ask some.
Yeah, I think sensitivity and specificity are difficult concepts for the public, but
yeah,
sensitivity, and these are talking 80 to 90s. That means that of all the people with a problem, this would pick up so much of it, 90% of it, right? And specificity would be, no, is that specific? Tell me.
That's right. That's right. So if you have, I'll say it a different way. If you have 100 infertile men, right, and you knew this, you just I know this, right? Our test can pick up 82% of it. Okay. And then of those, say it a different way, if you have 100 fertile men, we can accurately classify them as fertile 97% of the time. So we really weigh on the specificity, because what we don't want to do is call a fertile man infertile.
Right.
Right.
You have your priorities straight. That's good.
Yeah, I think that's right. I don't think we want to do that. Okay, so another question. Are you suggesting that targeted methylation abnormalities will lead to identification of potential treatments targeting those methylated genes?
Ooh.
No, I don't. Well, so do you understand the question, Paul?
Yeah.
Well, okay, so
that's a big one.
Wax philosophical and get a little dreamy. I'd say that's a potential down the road, particularly with CRISPR-Cas9 technology, which it's basically gene editing technologies, which now has been proven to work with DNA methylation as well. Well, works at least partially with DNA methylation. So there's a potential, say, if we see an abnormal DNA methylation profile in a region, we may say, oh, that's wrong. We know how to change that. CRISPR-Cas9 it. Boom, we're there. Now, decade away, if that. So Mark, what I was really referring to is the potential of using the information that we've gathered to help address how you might treat the patient with current available treatments, right? So in the case, there is a gene called Cas9, which is I get technical on you, but it's a calcium ion that is important for the acrosome reaction. Now, if we know that that's abnormally DNA methylated, right, then we know that there's probably a problem with that gene and that the acrosome reaction may be compromised. And so in those cases, what you might recognize is like, oh, well, they've failed at IUI a few times, then we recognize this might be the problem. Maybe what we need to do is go straight to ICSI, IVF, where you're injecting the sperm straight into the egg to get around that problem, so you don't have to deal with the problem of the compromised acrosome reaction. That's the kind of information that we're hoping that this test will provide.
I love it when you use big words, Alan.
So you're supposed to pull me back from the edge.
No, I mean, that question was definitely, and that was one smart reader listening who asked that question. They're like, holy, they were out there. They were definitely following along.
Okay.
But Mark clarified his question. He asked, will there be different patterns of methylation that pinpoint, hold on, don't tell me. Will there be different patterns of methylation that pinpoint specific focus, foci? Does that mean genetic foci? Yeah, I would say yes is the answer. I mean, you've selected a panel of epigenetic marks that don't represent genes right now. They represent a picture, an array, which you think is highly predictive of fertility, right? That's what you've done.
Right, but we're looking at
a huge pile of them.
Right, but the DNA methylation that we're looking at it resides in specific gene loci, right? So that gives us information about what's happening at the gene level.
So there is potential for pinpointing this to specific genes, like your acrosome Cas9 gene.
Exactly.
Yeah. So there, everybody.
If that Mark, does that answer your question?
Maybe that's Mark Hughes.
No, it's Mark Perlow down at in Atlanta.
It's great, beautiful.
So I think he has another question for us. Do environmental factors like smoking, marijuana, heat exposure affect methylation patterns? I think the answer is yes, but we don't have. I think that's a story that's still being played out, right?
Yep.
Yeah, those are
I can imagine when you use the word lifestyle, that's what you're talking about. Diet, social, recreational drugs. I think that's the mechanism by which they could cause infertility.
Yeah, and I think that's what that gastric bypass study showed pretty clearly, is that
yes.
If you have very dramatic shifts in environment, which the body is weight change is a kind of an environmental factor, at least on the epigenome, then the environmental factors do play a part. And there are lots of studies being conducted to understand how smoking impacts the epigenome.
So is this actually evolution?
Oh.
Is what we're saying?
No, I'm not biting. So I mean, I think it's perhaps an adaptive mechanism, right? I think it's a way for our body to respond to its environment. I think it's an adaptation, right? Kind of a near-term.
But why would you put those things in sperm? Right? Because you're looking at the sperm of men who lost a lot of weight and the epigenetic profile. You're looking at men at one age, and then 10 years later, you look at them when they're 10 years older, and the sperm are different. The epigenetic marks are different. Is that evolution? That's evolution. Come on, it's got to be. What else is there? That's evolution. The genetics hasn't changed.
Well, it's certainly. I think it's reflective of it's a map of environmental exposures, right? That are probably and probably alter gene function appropriately to deal with that, right? That would be my guess. And
we know that about half of human evolution is neurodevelopmental. So you see movies, Martian movies with big heads and big eyes. That's exactly where we're evolving. We're not evolving fingers and toes. We're evolving in our brains. And it looks like from Doug Carroll's study in sperm from, that's where it was happening, in those same neural developmental genes like autism and schizophrenia. And it's just fascinating. And that's heritable, right? That can be passed down if it's in your sperm.
Yeah, I mean, so there's lots of debate. I think we should be honest here that there's lots of debate about how heritable this stuff it can be, because there's very clear evidence that pattern of DNA methylation goes through erasure, right? It gets wiped out, and everybody for many years thought that it was just completely cleaned out, right? Like a disk. It was just completely erased, and then it was reprogrammed once the embryo started developing. Now, what we know now is that that's not entirely true. Actually, about 20% of DNA methylation is maintained. After that full-scale erasure, right, it's still maintained. And whether that's meaningful information or not, I think that's still playing.
I'm sure it's meaningful somehow. I'm sure there's a reason.
Yeah, I think the evidence is beginning to roll in that's really supporting this concept that these things are absolutely heritable. And in fact, that's what epigenetics by definition is. It's these marks on top of DNA that are ultimately heritable, across cell division and across the germ cells too. So
epigenetics is actually any alteration of DNA that doesn't alter its sequence.
Yeah, that's right. That's right. That's right.
So this is a parallel universe, and it's, how old is it? How old is epigenetics? How old is this study, this field?
Oh, the field of epigenetics. Well, I mean, so Charles Darwin had an interesting term for it called gemmules. And these were different little factors that would flow through the bloodstream to the gametes and change how the gametes were and then ultimately heritable. That's how you inherited changes from acquired traits. It really became much more after the genome was mapped, right? I think then we began to develop technology. So the ability to actually do anything with epigenetics is only several decades old. It's not a particularly old science. So I think there was a lot of uphill battle to deal with the, because for up through the 90s and aughts, for that matter, genetics was where it's at. GWAS studies was, you couldn't throw a rock without hitting a principal investigator of a GWAS study, right? Those were common, and so those are a little less popular now, and we really tried to understand what. So those were genome-wide association studies. We're trying to understand how the genome makes us who we are and how disease. That's what those studies were about. The problem was that many of the things that we were looking at, like complex diseases like autism, just hasn't played out very well with genetics. I mean, I think there are genetic components to it, and no, most certainly, right? But I think that epigenetics is going to be a lot more informative as we move on.
I was listening to David Page at MIT talk at the NIH last week on how men and women have sex-specific differences in response to disease.
Yeah.
So he's saying that the same mutation in a woman and a man would lead to different diseases and different trajectories of disease, and we should start thinking about them as not having the same genome, or having the same genome but different expressions of it. And he went on for an hour, and it was absolutely humiliatingly beautiful talk about his thought for the last 20 years. But the meeting was about how fertility could predict your health, or how it could be a biomarker. And he ended up saying as his last sentence that he thought that it was epigenetics that would seal the deal and be able to figure this out. Why we have differences in response to diseases or gene mutations, and why women get more lupus than men, and why men get more schizophrenia than women, etc. And it's fascinating that the father of the Y chromosome and the Human Genome Project thinks that the future in figuring out disease and health is in epigenetics.
Yeah.
Fascinating.
That is fascinating. Yeah. So what do we have? So I'm looking at more questions. We have lots from Mark.
We love questions. We know all the answers too.
Well, you might. I'm a scientist. I continue to look for answers. So I think he said, I think you said that with ICSI, the acrosome is affected, so the reports will not be a simple yes or no. You report known gene level issues. Yes, that's right, Mark. So if I can just kind of describe what our report might look like, and it's something we're working on, and I just want to be clear if there are people tuning in wanting to know a little bit about our validation study. We do have much of that data in hand, and we look forward to sharing that with people, but we're just not at a point where we can discuss the results yet. But we have been working on developing a report, and basically what you'll have is a score at the top saying, are you infertile, or there's a kind of a scale. It's from -1 to 1. So if you're above 0 to 1, then you're in the fertile category, and depending on how close you are to 1, the closer you are to 1, the more confident we are that you're part of that fertile group. Same thing with the negative. So if you're in the negative category, you're infertile, and the closer you are to -1, the more confident we are that you're part of that infertile group. And so you'll also see all the people that we've looked at, and you'll see the histograms of the different populations of people that we've already looked at. And then below that, I think, Mark, this is what you were pointing at and maybe interested in. We will have this list of genes that we've used to classify people. And the genes will show you if your DNA methylation gene is normal or abnormal. And then we'll tell you a little bit about what those genes are important for. And so many of the genes that we've looked at thus far that contribute to the score pretty significantly appear to be very important for fertility, and maybe not surprisingly. And I should say that's actually fairly comforting, because we approached this study that we did very differently. We basically said, look, we don't care what genes are involved. We're going to be very agnostic. We're just going to say, are there differences in DNA methylation between fertile and infertile men, right? And we don't care where they are, and the most important differences, we'll look at those and we'll use that to create this algorithm for discriminating between the two populations. And so we had no idea. We didn't go in and say, okay, we're going to look at this gene and that gene and this gene. We didn't do that. We were completely agnostic, and we said, what genes seem to be most important for discriminating those two groups? And it just so happened that many of these genes are important for fertility. And so, and again, we'll talk more about this as we can talk about our validation data. But yeah, many of the genes that we see to be very important for making that discrimination are very important for fertility in very different ways. So everything from the acrosome reaction to oxidative stress to other developmental stuff too. So I look forward to sharing that in more detail.
Yeah, I think that each of these genes is someone's career in science. I mean, this is a whole new thing, and you're just doing the 30,000-foot view to see if there's any relevance to the whole field. And, your first study was incredible, the one published in Fertility and Sterility, showing these precision and accuracy and the power of it. And now that looks like the prospective study, can you say, is it backing up what the retrospective study is doing? Does it look as good? Does it look as strong?
Nice try. I can't say.
Okay.
I'd like. I'd rather not. Yeah. Things are going well. I mean, things have gone very smoothly with the study. We've been very, very appreciative of the clinics we're working with Mark's group, particularly down in Atlanta. I mean, they've been very hugely contributive to what we're doing. It's been a huge effort amongst many clinics, and that's gone very smoothly. And we are very happy with having our results coming in, and look forward to talking.
Yeah, one of the most important things when you're introducing a brand new test that's once in a generation maybe is it applicable to all patients in all geographic regions, right? So you want it to be generalizable. So it's really important that these specimens come from all over the country in groups, and not just sort of LA or San Francisco or Colorado but then that's what you have is a very good wide distribution around the country of different samples. And you could even do that analysis, but that is going to make it much more generalizable.
Yeah, I think that's one thing that we tried to do is make it both geographically quite diverse, and I think it's very ethnically diverse as far as we can see. We also asked a number of questions of the patients too about both their obviously their fertility history, but also general health history, exposure history, so environmental exposures, obviously, and then also well-being. So we capture a lot of additional data about things that might affect the epigenome too. So we look forward to looking at correlations between those data as well as the epigenome.
So we've gone really deep, and I guess I want to bring it back to why would I order this test?
Yeah.
You have a little box there, and it looks cute like a Tiffany's box, but why would I order it? And I was thinking, as we've gone through the evolution of this product, it's ordered if you can't explain why a couple can't conceive naturally. That would be, one of the test question. That would be B. I don't know if I'd order it to explain why the semen analysis is abnormal, because we don't have that information. I would just, if the couple's having trouble and there's no apparent cause, unexplained infertility, that would be a reason. If a man, I might order it for this, if a man is smoking pot and cigarettes and has a terrible lifestyle and is failing to conceive and has a low sperm count, it may be a way to explain functionally what's happening to a sperm because of lifestyle issues, and maybe that would be a inspiration for men to change the toxicity profile of their life and clean it up a little bit, because men need numbers to do that.
Yes.
We don't know if that's going to help, but it's something that I think about. And then I would think about if you go through IVF and nothing, and it doesn't work, and it might be characterized by poor embryo development, and you don't get embryos to transfer, you might consider it instead of a fragmentation rate, which has sperm DNA fragmentation rate has been around for 10 or 15 years, but I don't know if it's been all that valuable in that situation. And I think for most of us, reproductive endocrinologists and reproductive urologists, it hasn't really been a go-to explanation for things in many cases, even though it would seem to be. This might be a more powerful tool for that, and I think it will probably explain more cases. Can you think of other reasons why a doctor or provider would order this test? Those are three reasons.
Yeah, so I think so I think much of what you said is correct. I think the other scenario is upfront, right? If you're doing an initial workup, you know as a couple, you come in that you do have a fertility problem, right? That's relatively easy to diagnose, right? You haven't been able to conceive over the course of a year. Understanding why is very tricky. And I think understanding why can really inform the path of treatment. So I think if you were to take this test right up at the beginning, you might understand a little bit more about what might be causing the infertility within the couple, right? And then you can use that information to guide the treatment and help counsel the patients as well. So I think this is probably a test that would be, I think in the beginning, I think it's going to be used for those hard to understand cases. So people that fail IUI several times or IVF even several times. But I think in the end, I think it's going to be very informative and useful when applied at the very beginning of the treatment process, when you're still doing the diagnostic workup. So then I think you're going to have a full picture of what's happening both for the male and the female. So that way you can understand which treatment options they have at hand.
Right, and there you might be able to streamline the care a little bit and avoid certain things that are probably not likely to work, and go to things that might work,
Right.
Which may, it could relieve a lot of frustration. It could save money. Streamlined care is always encouraged. It reduces morbidity and a sense of quality of life issues, because some couples go on for years, and some of them can't move forward without a good explanation. They just
Right.
And we're always scratching our heads. I'm going bald scratching my head, Alan. We need something.
Looks like you have a full head of hair there. Yeah, I think that's what I've heard a lot of, both from treating physicians and the patients, right? It's very frustrating not to understand why this might be a problem for people, right? Or what may be causing the infertility. And particularly in cases of unexplained infertility, I think it sounds like it's very frustrating. So yeah, we at least want to shed more light on that.
So Alan, I'm going to be giving a big keynote speech to the traditional Chinese medicine and alternative medicine, complementary medicine group in Vancouver next weekend, integrated fertility symposium on basically mostly on epigenetics, not a lot on this assay. But the question is, can they order this too, or who could order this?
So I think what we're thinking of right now is that this would be a physician-ordered test. So it needs to be an MD. But that being said, if someone doing alternative forms of medicine is collaborating with someone that's an MD, then I think that's a possibility. So right now, what we're planning to do is use this or provide this test to people working in fertility clinics, so reproductive endocrinologists, urologists such as yourself. I think OBGYNs will understand this as well. I think that's a possibility as well. Primarily people focused around fertility, but I think as we move out and move more broadly, I think it's other physicians that have an interest in understanding what might be at hand for patients suffering from infertility, and so I think primary care physicians could order it if they wanted to. But I think right now we're planning this to be a physician-ordered test.
Okay.
Yeah. So I think we've been rambling for nearly an hour. I know, Mark, you've asked
some damn good questions.
Some really good questions. Is epigenetic variation seen in bacteria? Do bacteria, do they have DNA methylation? Do they? Okay. Yeah, I don't know. I don't know the answer to that, to be honest. So I don't know. I mean, so I can't speak any more to that. I don't know about that.
I think I want to thank everyone for listening to our breakfast conversation about a very sophisticated field in genetic medicine and genomics called epigenetics, and how we're applying it to potentially figure out whether sperm are fertile or not, with the CEO of Epesona, which is the epigenetics company that's the vanguard of offering this. And I'll be available certainly over the weekend in Vancouver if you want to talk about, answer questions. And also my blog has something about epigenetics, Turek blog on Google. And my site has a lot about infertility at theturekclinic.com. Alan, do you want to say anything in parting?
Yeah, no, I again, like Paul, I appreciate everybody taking the time to listen to us talk about this. And we're excited about this test. I think hopefully it'll provide a lot of promise, or a lot of hope and opportunity for people. Once if you're interested in following along as we finish this validation study, again, you can probably go to our website and sign up from our product page. We can send you updates as things move along. And we will certainly be updating people, and we'll be talking about it at upcoming conferences as well.
Yeah, and epesona.com is a very informative site. It's got very good English language, non-scientific language to explain things. And,
it's far less scientific than me. It's less sciencey than me, right?
Yeah, it's great. And so epesona.com is excellent, and it'll probably have the trends. There's a blog on there, so you can keep in touch. But this is a game changer, everybody. And we're really happy you joined us today.
Yeah.
It's really a very new thing.
Yeah. Thanks, everybody. Really appreciate your time.